Hello everyone. We will be solving one more problem on particle kinematics, and this time we will have a situation where the acceleration is no longer a constant, it is a variable acceleration. Okay, so here is the problem for us. Now, to save some time, I have already drawn the figure for this problem, so I'm just going to pull that up now. Okay, so here is the situation. Okay, and what's going on here is the following. So I have an initial situation where there is a box which is placed on a bed of springs. Okay, the spring stiffness is not necessarily important to us because we are still not doing anything with regards to the kinetics of the problem. We are still involved in the kinematics, which is the geometric details of the problem. So we are not interested in that. Neither is the mass of the particle of any interest to us yet. Okay, what I'm told though is that at the initial position, this box or this particle has a certain velocity. Okay, so I'm told that the particle is pushed down with a certain velocity which is given as v naught. Okay, what happens if you have a particle sitting on a bed of springs and you push it down? It's obviously going to go down, right? Which means that in this final position, what happens is that this is compressed to a certain distance, and this distance is given as sm. Okay, I'm going to mark the distance starting from here all the way on to here. This is not necessarily the final position. I'll tell you why. Okay, this distance is given to us as sm. Okay, now this is not the final position, but this is the position before the box actually retracts back. Okay, so in a sense this final position is so the position at which the box retracts back, which means that this sm quantity is the maximum distance that this box can be compressed. Okay, this is the maximum distance the box can be compressed before it retracts back. And you can evidently see that this is a vibratory system. So if I give it an initial velocity, it will get compressed to a certain maximum distance and then bound back up, and then this will keep on oscillating back and forth until perhaps if there is friction or if there is any kind of air drag, then this will slowly come back to its equilibrium position once again. Okay, and we are further told that in the process of traveling from its initial position onto this maximum compressed position and then turning back and so on, the acceleration of this particle is a function of the position s. Okay, so first of all we have a position coordinate here, which I'm going to label as s. Okay, so this is the position coordinate, and I'm going to call that as s. Okay, and s is the position coordinate, so s is the position coordinate. And we are told that in this problem the acceleration is a function of s. Okay, so we are given that acceleration a is a function of s, and the relationship is g minus some c times s. Okay, and in this case g is acceleration due to gravity, and c is some constant. Okay, some constant which we are not necessarily told anything about, but perhaps maybe we might have to find it or do something of that sort. Okay, so I'm getting ahead of myself here. All right, so what are we supposed to do in this problem? In this problem we need to obtain the constant c as a function of the problem parameters. Okay, so obtain the constant c in terms of the problem parameters, which means that what are the problem parameters? Okay, so which means that the problem parameters are the following. They are the initial velocity v0, which is the initial velocity. Then I have this distance sm, which is the maximum compressed distance. And of course the acceleration is a function of the position s, but it's also a function of acceleration due to gravity. So g is also a problem parameter for us. Okay, so that's a keyword here. So what are the problem parameters? And these are the problem parameters, which means that I essentially need to obtain. So this means that I need to obtain C as a function of V0, Sm, and G. Okay, and that's the main idea in this particular problem, and you'll see that it's fairly straightforward. Before I dig into the problem, the first thing I notice is that, hey, in this problem, acceleration is a function of position, right? Which means that I need to think and see, okay, what kind of equations could I probably use in this problem? I have some information regarding acceleration. I have some information regarding initial velocity, which is given to us, right? This is something that is given to us. Perhaps maybe before we solve the problem, actually, I'll take a step back. I'll write out the things that are given to us, okay? Forgive me for that. So we are given, okay, we are given V0 and Sm, okay, and we are also given acceleration due to gravity, G. Okay, we are given all these things. We just need to find C as a function of all of these variables using the information of the problem. Okay, and the first thing that comes to mind is, okay, what kind of a relationship can I try to obtain between acceleration, velocity, and position? Okay, and here is typically what I do. Okay, I start off by saying, what are my particle kinematics equations? I list them all out. Okay, so start by listing all the particle kinematics equations for rectilinear motion. Okay, what are these relationships? I have A is dv by dt. Then I have V is ds by dt, and then I have A is V dv by ds. Okay, these are the three things. Then I look at the problem. Which of these three equations are relevant to us? Okay, which of the three equations is relevant to us? That's the question that I think about and see. Okay, what am I told? I'm told something about the acceleration. It's known as a function of distance. I'm told something about the velocity. I'm not told anything about time. So probably equation 1 and 2, which both deal with time, is of no interest to me at this point in time, pun intended. Okay, so since problem tells us something about A and V and S, but no mention of time, only equation 3 is relevant. Okay, and I mean equation 3 right down there. I'm just going to put an arrow and say, okay, this is the equation that I'm actually interested in. Okay, all right, then I pull out that guy and then say, okay, what am I going to do with that? Okay, so we start with A is V dV by ds. Okay, then what do I do? Okay, in our problem, acceleration is known as a function of position. Okay, so we know that A is given as G minus C times S, which means that the first thing I do is I cross multiply the denominator and bring it onto A. So this is, in this situation, A is actually a function of S. You see that, right? Which means that I can say, okay, ds times A is equal to V dV, or conversely V dV. Okay, conversely V dV is A as a function of S ds, which means that I'm just going to substitute and start integrating. I'm going to integrate from an initial velocity to some arbitrary velocity at this some point in time t, and that's going to be V dV. And then I'm going to have on this side integral from some s naught to some s, and A as a function of x is s is nothing but G minus cs ds. Okay, now just as a semantic point or a point of rigor, in reality I should not be writing my integrals this way. I should not have the integrand as ds, and then I should not have the limits of my integration have the same variable. I should in fact employ a dummy variable to be rigorous. Okay, but I'm not doing that just because this is it's going to be more confusing, and we have enough confusion coming ahead of us anyways. Okay, so I just want to make a point. Okay, so maybe a quick note for those mathematical aficionados out there. Okay, so note, I am skipping the use of dummy variables when integrating. Okay, all right, so what do I get from the integral? Then I see that, okay, this is going to be v square by 2 minus v naught square by 2 after the limits of integrations have been substituted. This is going to be, I guess before I do the substitution, this is G times S minus C times S square by 2, and the limits of integration are S naught to S. And if I do the further substitution, this is going to be v square minus v naught square divided by a factor of 2. This is going to be G times S minus S naught minus C by 2 times S square minus S naught square. Okay, so this is the expression that I end up having. Okay, I'm just going to put a box around this. This is what we're going to be playing around with. Okay, and complete the box, and you will see some of these expressions that I have actually derived in my elaborate lecture notes that I've posted on Carmen. All right, so what do I do? Back to our problem. So from our problem, what do I know? I know that at t is equal to t naught, which is equal to 0, let's say, so start from t naught is equal to 0. I'm just going to assume that, okay, because nobody says anything about t naught. I'm just going to assume it to be 0, and then I'm going to say, okay, at t is equal to t naught, here is the information that I have. So at t is equal to t naught, v at t naught, which is given to me as v naught. Okay, s at t naught, I'm just going to say this is 0. Okay, this is typically called as s naught, but it's 0 because I don't have any displacement from the reference at the start. Okay, then at t is equal to tm, that is the location at maximum compression, which is called as SM. Okay, the location at maximum compression is SM. What is the velocity at t is equal to tm, that is going to be 0 once again, right? If you remember the problem that we had solved previously on particle kinematics, if I take this box and I push it to the maximum position right before it's going to start retracting back, its velocity is going to be 0. But keep a note of the fact that its acceleration is not 0. So velocity being 0 does not necessarily imply that the acceleration is 0. That is an important point to make a note of. Okay, so note this. I'll maybe write this in red so that it's bright and shiny for us. Velocity being equal to 0 does not mean that acceleration is also 0 at that instant in time. Okay, and that's something to keep in mind. And this is a very simple example. Is you take a ball and you throw it up in the air. Okay, at the point at which the ball is going to return back, what's its velocity? Its velocity is 0. At the point at which it's going to return back, what is its acceleration? It is always subjected to acceleration due to gravity, which is trying to act vertically downward. So at the maximum position for the ball, which is traveling up and trying to come back vertically, the velocity is 0, but the acceleration is not 0. Okay, so these are the things that I know, and this is the information that I can probably use in our equation. Okay, so substituting for us into our equation, substituting into our boxed equation above. Okay, I have V at Tm is equal to 0, and then S naught is equal to 0, and so on. And so here is what I end up getting. Okay, so this is going to be 0 minus V naught squared by 2. Okay, and this is going to be G times Sm minus 0 minus C times Sm square minus 0 divided by a factor of 2. Okay, do not forget that factor of 2, which means that I can solve for C. Okay, so solve for C, I get C as the following. It's going to be V naught square plus 2G times Sm, all of this divided by Sm square. And this is the answer that we expect. And one thing to keep in mind is that here acceleration is not a constant, which is why we had to perform the integration in the following manner that you have seen. Okay, and the note that you want to make to yourself is, okay, acceleration is not a constant, so acceleration is given as a function of position. Okay, so here acceleration is a function of position, and hence the steps that we took to solve this particular problem. All right, and this is eventually here we have obtained C as a function of the variables of the problem, which is V naught, Sm, and then G. All right, thank you very much.